Hello, beautiful people. Today, I would like to share some learning, basically, an introduction to a tool called as LTspice. So, this is my content for today. So, I would like to cover what is LTspice, the steps followed, and whatever the steps I have followed to understand the tool better. So, I will give that information here. Then, different tab option under LTspice. Then, one specific example I will try to cover, that is NMOS, MOSFET, IV characteristics I will try to cover, and even I have a demo. Sorry, I have a demo for that as well. Then some specific examples over there, like PMOS and NMOS circuits. Then finally we will conclude. Along with that, I will give you the references that I have referred. Okay, good. Then let me get started with the LTspice. What is LTspice? Why do we need LTspice? By the way, this is how it looks like. The first window of LTspice will look something like this. And LTspice is a simulator, basically, as the name suggests. And it's a spice-based analog electronic simulator. And it's basically a software. And the important part is it's an open source. Okay, so you can use wherever you want and whatever you want inside that. And basically, this is currently owned by Unlock Devices. Before it was part of Linear Technology. Yeah. And what we can do here, as the name suggests, like it's a simulator and you can pass many inputs over there. Like if you have a third party models like the model from TSMC, if you want to pass and if you want to see how it behaves, you can do that. Or let's say I want to modify some of the parameters like VT of the device or something, that is also possible here. So it's flexible in that sense and it's very straightforward. And why I'm covering this video today is because some of my colleagues were not familiar with this tool. So whatever I learned recently, I thought I will make this video so that it will be useful for them. And the last part is some of the companies, in fact, the institutes like BITS are encouraging their students to learn the circuit aspects while learning, maybe while doing their masters. They are requested to go through the practical lab experiments also. So along with their theoretical knowledge, they can do experiments with ease with the help of this particular tool. That's why I said it's powerful and it will be useful in some point of time. So it will be a good thing if you know what is LTspice and how to use in future days also. Yep. It will come in handy in someday or the other. That's the point. Okay. Then currently in this particular video, I will cover this third point where I have taken a dot lib. When I say dot lib, it's the characteristics of the device are kept in a file called as libert. You can say dot lib file or liberty file or something. So library file, sorry, it's not liberty file, library file. So in the library file, we will have characteristics of each and every device. Let's say I have an NMOS. What is the VT of that device? Uh, what is the thickness of the oxide and all? Those sort of things I will try to cover. I have an example. I have a slide to cover that part. So currently will cover with respect to this aspect here. Then we have steps followed here in this second part of the this video. So I have taken the reference of these slides and everything from here. So you can refer this particular uh, link. You'll get all these details here. So we need to get specific models. So the first model is for the schematic view. So if you want to view the NMOS, I have taken it from CMOS N, and for PMOS, I have taken from CMOS P. That's the schematic names they have given. And again, as I said, I have taken the dot libs from TSMC 180 nanometer. So 180 nanometer is the target for me currently. So I am using the dot lib the library file from that, and the characteristics are based on 180 nanometer. That is the gate length of the minimum gate length of the devices over there. Okay, and yeah, as I said, these are the symbol views, the starting through. Then the last one is the model file from TSMC. And make sure after loading all these things and after keeping them in the specific locations as specified here, you need to relaunch your LTspice because it will read the database what is available in your installed location. That's why you need to relaunch your LTspice. Okay, don't forget that part. So here is an example of a model file from TSMC. As you can see, this is an example for NMOS, CMOS N for NMOS, and there are at least 20 plus device characteristics here. And the most important ones are something like VT of the device, that is threshold voltage of the device. It's being 0.366 here. And what is the thickness of your oxide? It is 1.7 e power of -9 um, meter or something. Then normal, what is the T normal voltage? Sorry, T normal temperature at which these parameters are kept. And again, there are plenty of parameters. Again, this is specific to Foundry. So they will give all these parameters for the users. Okay, this is just an example. Then let's go to the steps followed. So basically, I have installed my LTspice with this version from the uh, location that I have shared before. I mean to say the reference a link. You can go through that. Even I will put that in the uh, description below, so you can refer that as well for downloading the LTspice at your end. It works for both Windows and uh, the other part also. Okay, it's a handy tool in fact in that sense. So after double click on the window, this logo of LTspice, you will get this particular window. You can go to files and new schematic. Then go you can go to a option called as .op, that is for operating points or something, you can say. There you can include your tsmc018.lib file, that is the uh, library file for the characterization that you can include, and the format is very strict, like you should start with .include only, then tsmc018.lib. That's how it works. And you can go to this particular symbol here, whatever you see as an and symbol, right? You can click on that. There you will get all the options, including the user defined ones. So currently I have or third party defined one. Currently I have selected these two, that is CMOS N and CMOS P. That's why you see here. The built-in options are also available, and you can refer that later for as per your need. And one a built-in option is for voltage source that you can select by selecting voltage here. Yep, you can directly search here for voltage, you will get that option and you can put it over there in your schematic view. Then you can right click on your device. If you right click on your device, you will get the option something like this. There you can specify what is your length. So since I'm working on 180 nanometer now, so I have specified the length to be 180 nanometer, then made being 1 micrometer here. Similarly, you can change the value of your DC source, that is here, the voltage source, by right clicking on that. You'll get the option here and you can mention what is the DC voltage. So I have selected 1.8 here again. Yep. Then the important part is whether you want to do DC analysis or the transient analysis or AC analysis. Currently I have selected an example for DC analysis. That's why you see .dc v1 point, sorry, starting from 0 to 1.8 and steps of 0.2. That's what here I just expanded that here. So the format is pretty simple here. So dot DC, then V1. V1 is the source voltage name. Then the first argument corresponds to your initial value of the voltage, then the final value, and the last one is step value. That is optional for you. If you don't specify, it will take the step value on its own. So here I have specified a step of 0.2. That's why it will give 0.2 steps and it will reach till 1.8 there. The final schematic will look something like this because I have included a TSMC library file and I want to perform DC. That's why you do see here. And I have biased my NMOS in this way, and don't forget to short your body of your NMOS. Otherwise, it will give wrong answers. Okay, keep that in mind. Then finally, we'll go for run simulation. And there are two options to get the waveform. If you click on the wire anywhere, you'll get a plot for the voltage. If you move your cursor on the terminals, right, there you will get the plot for current and the symbol will change in this way. So you will get to know whether you are plotting current or voltage in that way. Okay, it is pretty straightforward here also. Then after getting the waveform, you have an option to check and get the exact value of the voltages or the currents in this way. So you can right click here on the waveform window and you can change the color also, default color to some other color if it is not visible. Then one or two cursors you have, that cursor will look something like this and you can move around that so that you can adjust wherever you want and you can get the values in the box in the pop-up window here. And you have two traces where you can get the values of your current or voltage waveforms in two different places of your voltage waveform or the current waveform. Yep. Then there is another option where you can vary your voltages in steps also. So for that, you can vary the voltage, that is VGS, that is gate voltage to source voltage. Sorry, here in this way, where you can vary the VGS value in steps. For that, you need to specify the DC value while selecting the section of your voltage. After selecting the voltage section of V1, you need to pass within curly brackets VGS. That will be taken here as an input for step parameter. Then it will vary accordingly, and you will get the steps also for VGS. That is your input voltage. Okay. Even this is straightforward, similar to other simulator language, other simulators also. Okay. Then there is one more option where you can get you can put the label for your nets, right? Let's say I want to put a label for this input signal being V1. You can do that using this option. You can go to net name under the same option bar, whatever you saw on top right, that same option bar. There is an option to give the net name also. So using that, and you can also give the port type also. Don't forget that because we need to specify whether the port that you are selecting, if it is a signal port or an PG port. For that, you need to specify whether it is input, output, or in-out. For that purpose, it's important. Yeah. Then here is one more example of the waveform where I have plotted the input output characteristics of my inverter. It is also called as PTC curve. So here I have plotted for three different conditions where I have varied widths from 800 nanometer to 1.6 nanometer. That's why you see all these things. Sorry, the last one is 1.6 micrometer, not nanometer. Sorry for that. And depending on the color, you see the things. You will get to know which curve corresponds to which graph. So again, you can get that from the same tab option or on top, where you can go to view step legend. Then you can get this option. But there is a precaution here where this works only when single graph is selected for viewing. If you have multiple graphs, this option will be disabled by default. So make sure you have only one waveform that you are viewing. There you can get this option. Okay. Then just to summarize on the useful tab options, here are the options. So I have used run simulator. I've used bias. I have used ground. I have used components from here. Then operating point and parameter to change I have defined using dot option, then drag and move using this, then cut or remove option using this cut option here. And even here there is a copy option. You can copy whatever section of your things over there. Okay. And there is an option to move around. The shortcut for that being Control plus R. You can rotate your object after selecting them from this particular section of select component. Okay. Even that will be useful for you. Here is an example that I have. Here I just plotted the VGS versus ID curve for my NMOS, and it looks something like this. And this is what we were expecting. And this is similar to the normal graphs that we would expect in any NMOS technology, right? Not only in 180 nanometer. This is how it looks like, and same graph is obtained here, and you can get the BTS, sorry, threshold voltage. Wherever it starts here, it again starts somewhere here. It's 0.36 again, because that's what we saw in the tsmc.lib file, correct? And in that way, we just verified the values over here. That's how we do, right? That's why we say, like, okay, whatever you do whatever you learn as a theoretical thing, just verify that using the practical simulation aspects of it also. That will be more useful, is what we think normally. Yeah. And the important note here is v source is being 0 here, since this particular net, that is the source terminal of it, is connected to ground. Vs is 0, so Vg is being Vg minus Vs, and it will be equal to V1, because V1 is the source voltage, sorry, gate voltage, and source is connected to ground here. So that's how we should interpret the graphs here. And I have a demo. So let me go to my window. So here I have my LTspice shortcut. I have launched my LTspice, and I will go to new schematic. Then I will directly go for here. Then I will type CMOS N, and I will put it here. And I will take, sorry, I will take ground. I will put it here. I need one more ground. I will put it somewhere here. One more here for the other one. Then I will go to wire. I will connect this here. Then I will connect this in this way, and I will have my voltage source later. I will put that, I will get that as well, voltage source. So voltage source again, I'll go here, I will search for voltage I have here, then okay, then can have somewhere here, again here, then you can say connect to these two, then connect these two, then don't forget this body connection, that is also done. Then I will right click here. If you move your cursor over the voltage source, right, you will get an option, that one finger thing. So there you can give the value of 1.8. I've given a 1.8 voltage here. Similarly, I will give here also 1.8 for my drain voltage. Then again, right click here. I will give length to be 118 nanometer. Then width to be, let's say, 1 micrometer. So when I have given that, then I will go to here. I will say dot include gaps ASMC N. I don't remember the one exact one. Let's yeah, it's ASMC 018 dot lib. Okay, you can keep it anywhere, it doesn't matter, but make sure the format is proper. Again, I will click on that. I will go for dot DC, because I'm doing DC analysis, and I want to vary V1 in steps of 0 to 1.8, and steps that is anyhow optional, right? I will not give any steps over there, then keep it over there. So that's it. So this is um, my schematic view, and actually I will go for run simulation. Then let's check whether I get any waveform. So as I said, so this symbol, whatever you see here on V1, is for plotting the voltage waveform, and this is for my current. So if I simply click on this, I will get a graph, beautiful graph, where it says your VT is somewhere here, correct? That's what I was expecting. So that way I verified, like, this particular NMOS CMOS in is having a VT of 0.36 or somewhere near there. Okay, that's how this particular tool is useful. Okay, hope it's clear. Then I will come back to my PPT again. Then I'll take my pointer. So this is what we have seen currently, and there is one more example where we can plot the VDS versus ID graph as well. This is similar to whatever we learned before. And again, this so many graphs, whatever you see is just because of this step parameter that I've used for VGS here. So I've varied VGS also in this way, and because of each and every VGS1, VGS2, VGS3, VGS4, we have different graphs. And even this is verified that way. Yep. And the important part, which I was pointing at before, where don't forget to short or give a proper connection to your body. Bias your NMOS or PMOS is what my point is. So here I simply shorted the body of my NMOS to the source. Similarly, body of my PMOS to the source terminal here also. Okay, this is required. Otherwise, you may not get the proper curve or the graph over there. Yeah. So just to conclude, so we've got to know how to start the LTspice and why it is required. That I explained here. Then different options in the tool. Then I gave in demo on NMOS IV characteristics. Then these are my references. Please feel free to go through those things, and I will put this even in the description. You can refer that as well. So with that, thanks a lot for watching.